Alex. Alex, are you with us?
Yes, I'm here.
Okay, so we're going from the warm human Kumulipo to now the numerological and an elegant world of station locations and performance. And Alex is going to lead us through some of the work that's been done on where we might put the next generation EHT dishes. So take it away, Alex.
Thanks, Shep. It's one of the things I've really liked about VLBI is the sort of the detailed science right alongside the chance to learn about other places and other people. Thanks for the very nice talk, Larry. So on station locations and performance, a lot of people have been contributing their talents to this work. I'd like to especially acknowledge Dom Pesci, who I've been working with closely on some of the more recent analysis that I'll show in the latter portion of the talk. So the main focus of this slideshow will be these two questions: where to position future telescopes in terms of their contributions to the science capabilities of the ngEHT, and how sensitive should the individual station elements be. And so for context, many of you will be familiar with the layout of the EHT array, 11 stations at 8 geographic locations shown here. And when these stations observe in a VLBI observation, they sample the two primary science targets, M87 and Sagittarius A star, in this way. This is for 230 gigahertz. And these patterns are spatial frequencies that are sampled. The main thing to notice is that there are gaps in the coverage of the existing array. This coverage has been built up over time and was quite difficult and so to achieve. But the ngEHT, as I'll show later, will significantly improve the existence of these gaps and the coverage overall. And so just a little bit of how we've approached this problem. There is a lot of interest in new targets, which I hope we'll continue to hear about this week. But I think it's worth understanding where on Earth we can observe these two sources, M87 and Sag A star, with respect to existing submillimeter sites that participate in VLBI. And so the blue contours show for M87 where you have coincidence with at least two EHT sites, and the red ones for Sagittarius A star, obviously more towards the south. And the overlap between these tends to be mid-latitudes, mid-longitudes. However, we haven't in our survey restricted ourselves to those locations which can coincidentally see both sources with existing sites. We've done a worldwide survey. What's plotted here is the altitude over all the Earth, and flagged for a lower limit of 2,000 meters. It was asked yesterday, or pointed out, that you generally want high altitude to get above the atmosphere to aid in high frequency observation. And so among these locations, and with an eye towards locations which may already have an observing facility that could reduce the time to coming online, we've identified a large number of candidate sites. This map in red shows most of the ones that we've identified, and among these, I think the ngEHT is hoping to add approximately 10 new stations, possibly in stages, as Shep mentioned during the opening remarks yesterday. So the reasons that you would add those new stations, obviously to sample new features on the sky by filling gaps in coverage, A related reason is that you improve the instantaneous coverage or the snapshot coverage of the array. But there's other reasons as well. One that I'll get into a little bit in this talk is the resilience to losing stations, either because of technical issues or weather unrelated to observing conditions or aside from observing conditions, things like wind and precipitation. Additionally, you might add a station to enhance calibration. In particular, you might co-locate with an existing telescope, such as the LMT, to add network calibration capabilities. Could be a reason to add a station. Finally, co-locating with other facilities may be a reason to add a station, and that relates to multi-wavelength considerations for ngEHT. And so the way we've approached this problem is to model it, and we use EHT imaging for this. We start with an image of a black hole source with realistic brightness distribution, one shown here from Christian Fromm, which has the right angular size and total flux. We sample it with a test array and then add realistic noise and attenuation to our synthetic data. And we take that synthetic data and then calculate a number of metrics on it. And I'll go over some of those subsequently. Now, in our test array, when we reported last winter at the ngEHT meeting, we focused primarily on a full array. That is, if you were to take the one best image that you could manage, or the one best observation, with the largest number of telescopes, say the existing EHT of 11 stations plus 10 ngEHT stations for a total of 21. And how does that perform? That's the question we've asked previously. And so a new feature that we're bringing into the consideration is that we, for particular, for repeat observing or long-term monitoring, we may not always have the full number of stations available. And so losing stations statistically in terms of their technical readiness, the existence of wind at a site or the chance of precipitation is something we folded in so that our synthetic observations don't necessarily always have the full 21 station array. And just to show a little bit of what those statistics looks like, what's plotted here is the fraction of time versus month of the year that the EHT stations, the 11 stations, have wind less than 15 meters per second, generally above 90% of the time, although there's months of the year when certain sites have closer to 80% of the time where they're available. Okay, so station dropouts aside, we also care about the observing conditions, and at submillimeter frequencies, that's primarily governed by the moisture in the atmosphere. And so what's plotted here is the precipitable water vapor. That's the column of moisture above a site. And highlighted on the left are the existing EHT sites divided into northern hemispheres on top and southern hemisphere on bottom. And you see the seasonal variation in both hemispheres mirror each other. The dashed black line indicates 5 millimeters of water vapor, which is a nominal goalpost. Generally, we would want sites that have a median PWV below 5 millimeters. And indeed, our candidate sites generally have that property. So the remaining sites here on the right are all those stations which were mapped earlier in red. And you see that nearly all of them have times of year at least when they would be beneath that 5 millimeter mark. Now the PWV isn't necessarily what matters to us. What matters is the observing quality, and for that we need to determine the opacity, and we do that with a radiative transfer model, one that was developed by Scott Payne at SAO. What's plotted here is the submillimeter transmittance closely related to the opacity. And what I want to highlight is the green and yellow bands, which are the 345 and 410 gigahertz bands. I think generally the thinking is that frequencies above 345 gigahertz will be quite challenging for VLBI. And you can see in this plot that it's another step beyond 230 to observe at 410. And so generally, what we're considering in this talk is 230 and 345. We've calculated similar spectra for the remaining candidate sites. Now, these spectra, which form the basis for our observing simulations, we need to be mindful of the limitations of them. And one that we're actively working on evaluating is the grid resolution of the weather variables that feed into that radiative transfer model. What's plotted here is a map of the Hawaiian Islands with Mauna Kea shown in blue, where the SMA exists. And the red plus signs are the grid of our MEHT2 weather inputs. And we calculate our optical properties based on an interpolation of that grid. And so one thing that we are mindful of is the whether or not there could be local anomalies that affect the weather conditions at a particular site inside of this grid. And to assess that, we've developed some custom-built weather vapor radiometers, what we're calling a sky monitor, and we're making field measurements at sites. We have 3 that are online presently. Jose Gomez yesterday showed some preliminary results from the Canary Islands, and we're very happy to be partnering with those local groups to be making measurements on the ground at sites of interest. Just to show that this device works, on the left is a comparison from the SMA. In red, we have our in situ measurement, both from the tipping radiometer, which is the facility instrument at the SMA, and on the right from our sky monitor that we're using for ngEHT. And notice that both lines agree very well with the black cumulative distribution functions, which were predicted from our nominal pipeline for calculating weather conditions. Okay, so that's how we do the simulated observations. I'll just briefly define some of the metrics that we're using and then move on to some example results. So the 2 most basic are the number of detections that we get in an observation. On the left here, you see visibility amplitude for a synthetic observation plotted versus time. And this number of detections is simply adding up all of the points that are in that time elapsed over the course of a day or a snapshot, however long you prefer. On the right, what's shown is the noise on an observation versus baseline length. And for that, we're determining point source sensitivity. So taking some average of the noise to determine our noise floor. A slightly more complex metric, but one that we found that works very well is the Fourier filling. And this is a geometrical metric which takes the Fourier plane and the tracks which are sampled during the course of an observation, gives them a width that we've defined in different ways, and then normalizes it by a circle which is defined by the longest baseline that you could possibly have, here shown for 345 gigahertz on Earth scales. And what's nice about this metric, it naturally folds into account overlapping coverage. So it doesn't reward you for adding stations where you already have existing coverage. Finally, we've looked at beam characteristics as metrics, both the intensities of side lobes and also just the geometry of the main beam. I won't talk about those as much in this talk, although there is 1 or 2 slides that have them. And so With these metrics, we often compare them. And so side by side, what we have here on the y-axis is the side lobe ratio of the synthesized beam. And on the x-axis, the incremental filling. And the red dot is where those metrics, what those metrics are for the existing EHT at 230 gigahertz. And as we add one new station to the EHT, we have new data points, which are scattered here. And generally, those are moving to the right, adding filling to our Fourier plane, and also diminishing the intensity of the side lobes. And as we add 2 stations, we see that trend continues all the way up to 10 stations. Now, what's important to point out here is that along the way of adding 1 to 10 stations, you have overlap in number of stations. And so the selection of the right set of candidate stations, which leads to the best performance in terms of these metrics, is what we have in mind. You can have an 8-station array, for example, which performs quite well in these metrics, and also a 10-station array that does it. And so that's something to keep in mind. And this is for M87. We've looked also at Sagittarius A star, and there you may care more about the instantaneous coverage. So same metrics, but instead of considering an observation with a set of scans which have evolved over the course of the night, you're looking at a set of scans and the baselines in those scans, possibly even a single scan, which is snapshot capability. And so as you add stations, again, we see that both metrics improve, the side lobes diminish, and as the Fourier filling increases. Now, each of these data points, which are colored, corresponds to a set of possible stations, a combination of 10 up to 10 sites from that sample of the red candidate stations that we showed before in the map. And the way we choose among these is to impose a cutoff. We define some upper limit, which is based on the maximum metrics that we achieved during our synthetic observation, and we look only at the top set, which are the points on the lower right here. Once we have that top set, we can choose among these and be assured that all of the arrays which are in that top set are performing quite well. But the question still exists: how do you evaluate arrays which are performing well for different sources? And the approach we've taken is to union them, so that we want arrays that perform well for M87, but also for Sagittarius A star, as well as adhering to cost guidelines that we have based on the programs that we hope to propose to. And so we took this approach and we identified 2 what we're calling reference arrays for working groups to use and the challenge to use. Generally, I think groups have favored using reference array 1, and I'll focus a little bit more on that to come. But both are actually performing quite well. This is the coverage, and if you compare to the existing EHT coverage at 230, which we showed on the earlier slide, you see it's sampling nearly the full plane. So I do, in the context of those reference arrays, do want to encourage folks who may have not seen them to watch recordings from the earlier talks today on the ngEHT challenge and the 86 gigahertz work, which I think these all have important considerations for evaluating these arrays in the context of the science working groups. So with that reference array, the question becomes, how does it perform throughout the year, which we haven't shown here yet, and also what would happen if instead of adding the 6 or 10 meter antennas, which were used to select those arrays. What if we varied the aperture size or the sensitivity of the station? And so taking our ngEHT reference array 1 and looking at a few metrics, what's shown here for M87 is the number of detections we would have in January, April, July, and October. And this is with the 11 station EHT in black, what we call the ngEHT, but also comparing against the baseline, which are the hollow points, which is the EHT array, the base array by itself. And you see that the number of detections increases by about 4-fold between those two. This is accounting for dropouts due to station loss, which is the main driver for the error bars here. Those error bars correspond to 90-10 statistics. And so you may only have 18 stations in your 21 station array participating, and that's what's driving that wide range. In general, we find that due to a combination of technical readiness and weather, we lose on average about 2 stations during a synthesized observation. What you also notice is that the number of detections is fairly insensitive to the time of the year, at least for M87. And we find something similar for Sagittarius star, at least with the full track observation. But when we look at the snapshot, which is not a full night of observing, but a single scan, you do see more sensitivity to the time of year. In July, you have significantly fewer snapshot detections than you would have in, say, January or April. Now, these are the 2 primary science targets for ngEHT. We've also started looking, given the strong interest in news sources, at some example news source. And this was an idea, I think, that Avery Broderick initially suggested, which was simply to take M87 and scale its flux and size so that it was 10 times away, or the equivalent of 10 times away, 10 times further away. And there you see that the number of detections drops because of the lower source flux. Now, as we go to 345 gigahertz, and I can just flip back and forth, this is 345, 230, the number of detections, of course, decreases because 345 observing is more difficult. And you do see in M87 in particular some dependence on time of year, losing about half of your detections compared to April to July for the median values here. As we look not at time of year, but at the size of the aperture at the ngEHT sites, we also see that number of detections, at least for M87, is not particularly sensitive to the size of the aperture. This is for 8 gigahertz sidebands in April. For Sagittarius A star, you do see some dependence on aperture size, getting about maybe 50% more detections as you increase from 4 to 12 gigahertz with the full observation, full track. At 345 gigahertz, we are more sensitive to aperture size, to station sensitivity. You can see some slopes. These are log scale, so keep that in mind. But for M87 now at 345 gigahertz, you see that the trend is to increase number of detections as the aperture size increases, and you see that too for Sagittarius star. Now, number of detections is a little bit shielded from station sensitivity. What the trade-off really amounts to is how much you value your point source sensitivity. And so there we do see significantly more importance having a larger aperture at the news stations, particularly for Sagittarius star. Notice that point source sensitivity in the center plot is dropping by a factor of about 4 or 5 as we go from 4-meter apertures to 12-meter apertures. And finally, another reason that you would prefer to have the larger aperture at ngEHT sites is to improve the ability to operate not with the full 11-station EHT array, but with a subarray consisting of 3 EHT stations shown here. And there again, we see some dependence on the point source sensitivity as a function of our aperture size. On the M87 scale, the right plots, I have left those out for some of the more challenging cases like 345 and the subarraying. Detections in those cases on a very faint source may be more challenging and would require more study. So these metrics, number of detections, point source sensitivity, and filling factor, we do think about how they'll affect the real goal of the ngEHT, which is to improve imaging capabilities. We have done comparisons.
Alex?
Yes.
We just have a couple minutes left.
Yes, I'm wrapping up. We have compared those metrics to imaging metrics. What's shown here is how we think imaging can improve as you add ngEHT, a large number, 10 stations, showing here the instantaneous coverage of the array, and that translates directly to very high fidelity movie making. So this is for Sagittarius A star. The model has been blurred to the resolution of the beam and scattered, but we see our reconstructions match very closely. We're able to map flux as a function of time to high fidelity. And so the conclusions are that the addition of stations will enhance the sampling, and we're using Fourier plane metrics to guide that. I think feedback from the ngEHT challenge and the working groups on directing this work and what the key points are is very critical. And we're looking forward to hearing more about that this week. And finally, I think the new feature that we've sort of added to the analysis is that the availability of stations due to technical readiness and other considerations is a big driver for performance. That's all I had. Thank you for listening.
Okay, thanks a lot, Alex. I need to look at some of those plots pretty carefully. But do we have any questions from, I see Razi has her hand up.
Hi, Alex. Very fantastic talk. So we just got a quick question. I think that you mentioned that going to 345 gigahertz is just challenging and even above that for radio observations. Maybe I misunderstood that, but if this is like that, why ngEHT consider even going further up like 480 or 690 gigahertz? Why not scaling this down to, I don't know, 100-ish or whatever lower frequencies? Do you have any opinions about that, or did I misunderstand you significantly?
Thank you, Razi. It's a good question. It's very enticing to think about higher frequencies because of the higher resolution and other considerations. There have been some groups that looked at it in detail, and in general, getting detections on VLBI baselines is just very challenging because of the additional noise that you have and the smaller beam. And Razi, I'd encourage you, I'd be happy to put you in touch with some of the groups that looked at that in more detail.
Yeah, absolutely. Fantastic.
Okay, there's one question from Neil too. Neil.
Thanks, Shep. Thanks, Alex. There was a lot of information in there. Very, very interesting. I realized that the recording of this talk is going to be available, but there's just so much information that I don't think I'll be able to get a lot from just the recording. For example, when you simulated 3 HD stations plus the ngEHT and several other combinations, And your publication, your initial publication on site testing was really a useful resource. Is there some way that there's more information on all of this? Are you planning to publish or make a live document on it?
There is an effort to compile some. Thank you, Neil, first of all, for the good question and compliment. There is an effort to have some additional information publicly released as part of this and ongoing efforts. Shep, I don't know if you want to say anything more about that.
No, we're working on that. There is going to be a reference array document that Alex referenced, but there could be other memos in the nearer term. We can get some of this out more quickly. So we should talk more about that, Neil. So we're a little pressed for time here. LOC members, do we have time for one more question, or do we go right into the fireside chat?
Well, we can take a question. I think I'd prefer maybe to, after this, take a couple minutes for a break and then start the fireside. I might even cycle the Zoom.
Okay, do you want to start the fireside at 3:10?
That'll be fine.
Okay, so we'll take one more question from TK, and then I guess we're done for the day then, except for the fireside chat.
Okay, thanks a lot, Alex. That was a great talk. My question is a little bit off topic. This is about your water vapor monitor that you developed. I've not kept track of it. Is that something that has enough sensitivity and time resolution to be able to actually be used as for phase correction? I'm sorry if I'm completely missing the point here. Is that a possibility?
Thanks, TK. I appreciate the question. I don't think we've thought about that too much. I think the main goal was to do the validation and verification of the Merit 2, something to think about in the future, using it for other purposes. Haven't thought about it very much.
Yeah, I mean, given that it is so compact, if that's a possibility, that may be a very useful avenue to pursue. Thanks.
Okay, so we're gonna have to leave it there. I see you has his hand up, but I'd encourage you to talk to Alex a little bit later on this. So Lindy, I hand it back over to you and as LOC lead.